let's check sound and make sure I can hear myself. That looks good. Let's check for video. Do I see my hand? Yes, I do. Okay, we are good to go then. Time to unplug these headphones and get started. And for once, I'm actually here a little early. How about that? Hopefully this means I get to finish early. So, this might be a short one. We'll see how it goes. I don't have it like super structured or anything, so it's gonna be kind of like last time. I'm just gonna kind of remember what to present as I go. But I do have like some core ideas in mind. The plan for today is to discuss rotational kinetic energy and also just do some energy problems and talk about potential energy and how our new understanding of concepts like center of mass can affect that a little bit. And we'll talk about what else? I will want to talk about rolling without slipping versus rolling with slipping, and work done by a torque is another subtopic. We will look at that through a problem, most likely. It's not a very commonly required thing that you have to do, but there's no reason why you shouldn't know how to calculate work done by a torque. Anything else? If we go through things really, really quickly, like under, I want to say 2 hours, then we might go ahead and also do angular momentum. But I'm not betting on that. Most likely angular momentum will be next stream. So we'll see how things go. But without further ado, let's get started. Rotational kinetic energy. Rotational kinetic energy, as opposed to the kinetic energy that we've been dealing with up to this point, which is translational kinetic energy versus translational kinetic energy. Okay, so first off, the formula. If translational kinetic energy, Ke translational, is 1/2 mv squared, what do you suppose the rotational version of this equation would be? Ke R, or sometimes people call it Ke ROT, or just K. Ke is something I like to use, but I know the AP exam and textbooks like to use K. We've been over that before. We talked about it back in the energy chapter. But what do you suppose kinetic energy rotational is going to be? Just taking the translational version of it and substituting the variables with their rotational counterparts. Well, the rotational version of mass, that's the topic of last time. That's moment of inertia. And what's the rotational version of velocity? That's angular velocity. And that's it. It's as simple as that. Kinetic energy rotational is 1/2 I omega squared. 1/2 moment of inertia times angular speed squared. Speed in particular, because the magnitude is the only thing that matters, not the direction, just as it was for translational kinetic energy. Only the magnitude of the angular velocity matters. So angular speed is a term that you will hear a lot in problems. Angular speed relates to angular velocity the same way that speed relates to velocity. It's just the magnitude of the angular velocity. So really, really simple equation. Well, what complicates it is last time we saw that different objects have different moment of inertia formulas for them. So that's going to be where a lot of the work needs to be done before you can actually calculate. But now that we have this, we can expand our change in mechanical energy equation. So change in mechanical energy is equal to non-conservative work, the total non-conservative work being done on an object or system of objects. We can rewrite this as mechanical energy final minus mechanical energy initial equals work non-conservative, and add mechanical energy initial to the right-hand side, and you get mechanical energy final equals mechanical energy initial plus the total non-conservative work. And if the total non-conservative work is 0, congratulations, you just simplified this equation a little bit, and you have the equation for conservation of mechanical energy. I would include the work non-conservative in the equation anyway when memorizing it, just so that it's present in your mind in case you're faced with a situation where it's not 0. If most of the time you're faced with situations where it is 0, I don't think it costs that much to write it down and then strike it out as a 0. I think that would be a good best practice until you become really, really comfortable with identifying situations where mechanical energy is versus isn't conserved. Anyway, expanding mechanical energy final. So mechanical energy includes both potential energy and kinetic energy. So we had two different potential energies to consider. We had potential energy gravitational and elastic potential energy. Potential energy gravitational and elastic potential energy, or spring potential energy as I call it, PES. And we only had one kind of kinetic energy before. Well, now we don't. Now we have KE translational, and I guess for all of these I should be writing final. And now we also have kinetic energy rotational. And then for the initial side, we do the same thing. Potential energy gravitational initial plus potential energy spring initial plus kinetic energy translational initial plus kinetic energy rotational initial. And then, of course, plus any non-conservative work that might be getting done. So there you go. Now we have the full equation for change in mechanical energy, at least as far as mechanics is concerned. We would also add, if you were doing electricity and magnetism, we would also add two more potential energies here, magnetic and electric potential energy, and then the equation would truly be complete. But fortunately for you, you don't have to worry about that. This is as many terms as you will have for this course in this equation. So before anybody starts shouting, this isn't even my final form, as far as this course is concerned, this is the final form. This is the final form of this equation. So we're going to be faced with situations where the tricky part is going to be identifying whether an object is strictly in translational motion or strictly in rotational motion, or is engaging in both. It's not as easy as it might seem. It's not as easy as it might seem. When does an object have rotational kinetic energy? Well, I could have, for example, this yo-yo over here just rolling along the page, and this would have both translational and rotational kinetic energy. How do I know? How do I know? Well, it has translational kinetic energy because the whole thing is moving. Some people will say it's because its center of mass is moving, and that's not true because I have a counterexample for that. It's not necessarily that the center of mass has to move, it's the axis of rotation that has to move. If an object is rotating and its axis of rotation is also changing position as it moves, that's how you know that the object is engaging in translational motion along with its rotational motion. The rotational part should be obvious because it's, rolling around some sort of axle. Right, there's some sort of axis. I'll try and follow it with my pen. Yeah, something like that. I kind of like that it rolls back. That's an unexpected benefit. Okay, hopefully that made some semblance of sense for you there. But yeah, you see the axis of rotation. I held my pen above where the axis of rotation would be, and you see the axis of rotation moving. That's how you know that translational kinetic energy is happening. Rotational kinetic energy is also happening because there's motion around that axis, right? It's moving around the axis, which itself moves. So that's the scenario where both of these terms would be non-zero. Now I present to you a situation where the center of mass moves, but the axis of rotation doesn't. So here we have something that's just kind of nailed in place, held along some sort of axle, some object like this, and it is let go, and it swings down to here due to the influence of gravity. It gets nudged a little bit, and then it tips over, and the force of gravity carries it to this position. So I can actually model this with, let me grab a pencil. I can model this with this ruler. Well, at least the part of it that I can show on screen. So what I can do is I can stick this pencil in here, and we'll say this is, your axis of rotation. And we'll pretend that this ruler is actually standing vertically, and I'm holding it, and then I let it go, and then gravity carries it this way. Its center of mass moved, but its axis of rotation did not. The center of mass moved, the axis of rotation did not. The axis of rotation stayed right here. Well, at least to the best of my ability. My hand might have shaken a little bit, but in a real experiment, we would have something sturdier and something that is more stable, sits in place. But yeah, in a situation like that, in a situation like this, the only kinetic energy that we have is rotational kinetic energy being gained as the object swings down. Because while the center of mass may move, the axis of rotation does not. So this would strictly be rotational kinetic energy here. And this is going to lead to another kind of frequently asked question. Well, I don't know if it's frequently asked, but it should be frequently asked. This is going to lead to a little dilemma later once we do some trickery with the center of mass. So we'll be revisiting this scenario, this situation. So there's an example of something that is in rotational motion but not translational. And then we've seen plenty of examples of things that are in translational motion but not rotational. That's something like, I don't know, a block sliding across the floor. Unless, it's tipping over and rolling, which block-shaped objects don't tend to do, because any net torque you exert on them, we talked about this last time, you've got these two support points that keep it stable. It takes a lot of torque to tip it over enough to make it actually start rotating, because otherwise you nudge it a little bit, it tips over slightly, and then the torque due to gravity tends to bring it back. So you would have to exceed a certain amount of force, and more specifically, you'd have to exceed a certain amount of torque due to that force while pushing this object in order to make it tip over, which isn't impossible to do. If you've pushed furniture or boxes or anything, you know that if you push them really hard from the very, very top, you can get them to tip over. So it's not impossible, it's just more difficult. It's hard to do by accident. It's hard to do unintentionally. And I see that I misspelled rotational up there. I forgot an L. Rotational. This is why I'm not the English tutor. I don't even know how many times I've made that joke throughout this entire series, but I'm sure there's going to be somebody out there who goes out of their way to count, because there's always somebody like that on the internet. Anyway, so that's a scenario where we have strictly translational but not rotational kinetic energy. And then we have one more scenario where it can be either or, where you can view it one way or the other, but at the end of the day it can't be both. And that is circular motion. So if I have an object, it can be uniform or non-uniform, it doesn't matter, but let's say an object in uniform circular motion is moving around. You could say it's moving around an axis of rotation through here. Right? You could identify an axis of rotation for this thing to be moving around. And you could say that this thing has rotational kinetic energy about that axis. You could definitely say that, because if you take this object and you just spread out its mass over this circle, then that's basically the same as, a hoop or a ring. That would basically be the same as a hoop or ring spinning in place. Do I have anything even hoop-shaped here? Oh, I know. Let me grab it. I probably should have prepared this ahead of time, but here's something hoop-shaped. A roll of tape. Which, as you can see, I bought from Dollar General. I've had this thing for years. You don't use as much tape as you think you do. I've had this for I want to say 10 years. I used it a bit when I bought it, and used it a couple times after that, and barely used it at all since then. Maybe if you're moving a lot and need to tape boxes or stuff like that, or you buy a lot of jars and you need to label them. But now I'm going off on tangents. So here we have ourselves a hoop, and if I have some sort of axis of rotation for it to go around, then that's basically an equivalent situation. To just an object of mass m engaging in uniform circular motion around a point. So here, you can view the kinetic energy as being translational or rotational or both, I worded it wrong. You can view it as translational or rotational, but not both. That's what I was meaning to say. You can view it as translational or rotational, but not both. So let's take a look at what happens if we calculate its kinetic energy as a translational kinetic energy. Kinetic energy translational, assuming that its tangential velocity is v. What would kinetic energy translational for this object be? Well, it would be 1/2 of its mass, m, times v squared. Okay, what about its rotational kinetic energy? What if I treated this as having a rotational kinetic energy, K-E-R? Well, that's going to be 1/2 I omega squared. And what is moment of inertia for this? Well, this is a point mass. This is a point mass. So its moment of inertia is simply going to be its mass times its distance from the axis squared. Distance from the axis, that's the radius of this circular path. That's r. So 1/2, and then the I is equal to mr squared for a point mass. And omega squared, well, we know how to convert between tangential velocity and angular velocity, at least we should remember. That's something we discussed in rotational kinematics, the very first topic of this current chapter. V tangential is equal to r times omega. And of course, I might as well list them here. Arc length, distance traveled is equal to r times delta theta, and acceleration tangential is equal to r times alpha. We're going to use these a lot after this point in the course. Well, I should say, after this point in the chapter, you don't really use these very much in the remaining chapters. Well, you kind of use omega, but it's a kind of different thing in the next chapter. We'll talk about that when we get there. Anyway, these, make sure you remember them. A lot of students forget them for some reason. I don't know why. They're pretty simple equations. All you have to do is multiply the rotational version of the thing with radius and you're good to go. You get the tangential version of the thing. Speaking of which, I should have called that V tangential over there. But yeah, the omega squared, omega can be rewritten as V tangential over R. So omega squared is V tangential over R all squared. So this becomes 1/2 and then mr squared times V squared over R squared. The R squared cancels with the R squared, and we have 1/2 mv squared is what ultimately drops out of this. So you could view it as rotational kinetic energy and not translational, because you could think of it as an object that's moving around some axis and that axis of rotation doesn't move. That is certainly one way you could think of it if you don't want to picture it as a strictly translational situation. And I suppose that might be the more accurate interpretation of the two. But the point is, it's definitely not both. It's definitely not both. Okay, what about this situation where I take this mass and I spread it out over the circular path and turn it into a ring? Well, we said that the moment of inertia for a ring or a hoop is mr squared. I ring or hoop is the mass of the ring times the radius of the ring squared. So we would just be substituting with mr squared here anyway. At least with the ring, it's more apparent, it's more clear that it's only rotational kinetic energy and not translational. Because again, axis of rotation not moving, you basically have a spinning ring, a ring spinning in place. A ring spinning in place like this. Well, I mean, again, because I'm not very precise with my hands, you see the ring moves a little bit, but if I was more careful with this, you would see it spinning in place. So yeah, it's the same mr squared if you put it in the equation. V tangential of any individual part of the ring is still going to be r times whatever omega this ring is spinning at. So all of this just ultimately leads to 1/2 mv squared again. So yeah, for the circular motion situation of a point mass, you could interpret it either way, but not both, because if you're interpreting it both ways, then you are double counting your kinetic energy. You're claiming to have more kinetic energy than you actually do. I mean, ultimately, rotational kinetic energy is really just chopping the object into little pieces and calculating the translational kinetic energy of each of those pieces and adding them up. And that chopping it into pieces and adding them up is kind of built into this I over here, into the moment of inertia factor. And one situation where we can actually try and see that would be, I told you I was going to go back to this scenario over here. So there are a couple of things we can do with this situation over here. Let me actually redraw it on a new page. Let's open up a new page and redraw this scenario with some sort of stick or rod-like object that starts in an upward-facing position, like so, and swings down to this position. The task is to calculate what its kinetic energy will be at the bottom of the swing. Let's assign it a mass of m. We'll say that its mass is m and its length is L. And this is a rod being swung through its end. If you didn't memorize the formulas, it's okay. I did say you don't have to memorize them, but if you remember from last time, the moment of inertia for a rod rotating about an axis through its end is 1/3 of its mass times its length squared. So let's say that this thing started, well, how do I want to define height here? So I'm going to define my zero height over here. I'm going to define my h equals 0 line over here. Why here in particular? Well, that's where the center of mass is going to end up. So something interesting that we can do with center of mass is we can use it to figure out the total change in potential energy of an object as it spins. If an object rotates, we don't have to chop it up into individual pieces and figure out what the change in height for each part of the object is. we could do that. We could certainly, let's say, cut this into 4 pieces, for example. Here, 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 and here. I don't think that's a very even 4, but we'll pretend that these 4 pieces are equal in size. And we could say this piece traveled and went down, I guess, 2 diameters worth of height, and this thing went down 1.5 diameters worth of height. Hold on, let me actually draw that somewhere separate. So yeah, let's cut this into 4 pieces. And let's say that this piece swung down to, I'll draw it in a different color. What color should I use? Let's use this one. Actually, no, this one's too dark. Let's use orange. That way there's good contrast between the two. So let's say this piece moved down here. And this piece would have moved down to here. And that piece would have moved down to here. And that last piece would have moved down to here. And you could calculate the change in height for each of those moves. You could calculate the change in height. Let's say this is, well, we already defined the length of this as L. So let's say that this piece moved, at least its center moved by, let's see, it starts 1/8 of the length along the way and goes down to 1/8 of the length downward. So 1/8 above, right? This height over here is 1/8 L, L over 8. And this height down here is another L over 8, which I guess I drew pretty poorly. That is another L over 8. That looks like an I. That's not good. So overall, this first piece dropped by L over 4. So 1/4 of the mass went down by a distance of L over 4. So you could say delta potential energy of piece 1 is equal to M of piece 1 times G times delta H1 is going to be L over 4. Change in potential energy of the second piece. The second piece will have started up here and moved down to here. So it would have started, let's see, so that's 1/4 length, and then that's 1/2 of a quarter, that's an 1/8. So 1/4 plus an 1/8, this over here would be at 3/8 L. 3/8 L. And it would have gone from 3/8 L above to 3/8 L below this, I guess, axis, whatever you want to call it. So in total, it would have moved 6/8 or 3/4. So M2 times G times 6/8 or 3/4 L, 3L over 4. And then change in potential energy for the third piece, you can imagine, if you continue following the pattern, will be M3G times, it would be 1L over 4, 3L over 4. The next one would be 5L over 4. And then change in potential energy of the fourth piece would be M4 times G times 7L over 4. And so the total change in potential energy would be change in potential energy total would be, well, each of these M's, M1, M2, M3, and M4, if we're assuming that this rod is uniform, it's just going to be 1/4 of the total mass. It's just going to be big M over 4. So we have big M over 4 times G big M over 4 times G for each of these, so that is factored out, times the sum of L over 4 plus 3L over 4 plus 5L over 4 plus 7L over 4. So they all have the same denominator, which means I can add the numerators directly. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. So I've got 16L over 4, or 4L. So I get M over 4 times G, all times 4L. These 4's cancel out, and I'm just left with MGL. So we're saying this is equivalent to an object that has moved by a distance of L. This potential energy change, I guess I would also have a negative sign because it went from above to below, so I should have included a negative in front of all of these, but we'll say magnitude of the total potential energy change. There, that fixes it. And then magnitude there, magnitude there, magnitude there, magnitude there. There, that fixes the issue for those who were screaming at me to add a negative sign. So MGL, this is equivalent to an object of mass big M that has moved up or down, in this case down, a total distance of L. Well, there is something that moved down a total distance of L, and that would be the center of mass of the object. Now, you might say that I just arbitrarily chose to chop this into 4 pieces, and, I didn't take into consideration, for example, how the potential energy change for the top half of the first piece is different from what it is for the bottom half. Well, yes, but you could repeat this process as many times as you want. You could chop this into as many thin slices as you want. You could chop this into 400 slices if you want, and you're still going to get the same outcome. So one thing I would recommend for you to try is see if you can do this again with, let's keep it reasonable, do it with 6 pieces or 8 pieces, and you'll get MGL every single time. You'll get MGL every single time, because MGL is the total change in potential energy of the center of mass. This place right here is a distance L, or no, rather L over 2, is a distance L over 2 away from the axis of rotation. And it swings all the way down to a position that is another L over 2 below. So from L over 2 above to L over 2 below, the center of mass moved a total of L centimeters, meters, whatever units you want to use, away from its initial position. Its potential energy change has a magnitude proportional to L. I know that's not a complete proof, but hopefully this is enough to satisfy. You might argue that this only works because the shape conveniently happens to be a stick that can be chopped into nice symmetrical pieces, but think about it this way. Whatever the shape of this thing could have been, I'll draw a center of mass here, and then I'll draw some random blob-shaped thing, and say that it swung around this axis, and it swung down like this, and I guess I'm not sure how I'm going to redraw my blob, but I think you get the picture. If this thing was just some randomly shaped blob that swung down instead of a stick, well, then we talked about last time how at the center of mass, you can draw lines through the center of mass, and any line you draw through the center of mass should just split the mass evenly on both sides of that line. So you would have half of the mass is above this line and half of it is below. So basically, we're just repeating this same process that we did over here. Here I chopped the rod into 4 pieces. Here I'm chopping the blob into 2 pieces, and those 2 pieces, wherever their centers of mass are, maybe this one has a center of mass here, and this one has a center of mass there, you could calculate the change in potential energy for each of their centers of mass and end up with something like this again. And if you want to chop it even further, well, now you just draw more dividing lines and you find the centers of mass of these 4 pieces that you now have. Maybe this one has a center of mass here, and this one has a center of mass here, and this piece has a center of mass. I want to say it's closer to the right side, so maybe something like that. And this one has a center of mass maybe over here. And you calculate those changes again for those individual pieces. I think if you sit there and reflect on this a little bit, you'll be able to convince yourself that this makes sense, even though we haven't really proven this with calculus to be generally true for any shape. I hope that this is sufficient to convince you that the change in an object's potential energy when it swings from one height to another is simply the change in potential energy of its center of mass. It's yet another wonderful and convenient property of centers of mass. So, now that we are done with that detour, let's go ahead and calculate what the final translational velocity of this object will be. And also calculate what its rotational kinetic energy will be at the bottom of the swing, and also calculate what its final translational velocity will be. So we will assume conservation of energy here because the only force that's really making this system move is the force of gravity. There is a normal force acting on this thing. There's a normal force that's acting upward. This axis, whatever it is, it's holding the thing up, right? Without this axis, if you remove this axis, then it just falls. Well, it doesn't fall that way, but it falls, that way, down the screen. So I guess, can I even fit this in? No, I can't. Yeah, there's no way. But you all can visualize, I hope, what would happen if there was no axis holding this thing. It would just fall straight down. So yeah, there's a normal force being exerted upward by the axis, but there is no motion. There is no motion along the direction of that normal force. There's no translational motion specifically. There's no translation happening vertically up or down. The only upward or downward movement is happening because of rotation, not translation. There is no translation against or with the direction of that normal force, so there's no work being done by the normal force, so the non-conservative work is still 0. So I can say 1/2 I omega final squared plus 1/2 mv final squared. This is going to be 0. There's no translational kinetic energy here because the axis of rotation did not move. plus mgh final, or I guess I should be using the capital G, but we'll make the substitutions in a minute. And there's no spring potential energy to take into consideration, so we're done with that side. Equals 1/2 I omega initial squared plus 1/2 mv initial squared plus mgh initial plus the non-conservative work, which is 0. So the system started at rest, so this was 0. There's no translational kinetic energy to take into account here since the axis of rotation isn't moving, but also it started from rest anyway, so it's 0 either way you look at it. So we're going to have 1/2 moment of inertia for a rod through its end is 1/3 of its mass times its length squared times omega final squared, which is going to be I will rewrite omega final as it will be, let's see. Actually, I'll leave it alone for now. We'll deal with that in a minute. Plus mgh final, that's a 0, and then we skip ahead to mg, and then h final I'm going to say is 0 here. Equals mgh initial, so that's going to be mg, and then h initial from here to here. That's just going to be the full length of the rod, right? This was from here to here is L over 2. And then from here to here is another L over 2. Well, actually my L over 2 needs to be, yeah, there. That's better. So the total change in height is L. Okay, we can, well, I guess we could cancel the M here, but the question was, what is the final kinetic energy for the first part? What is the final kinetic energy? It's just going to be equal to mgl. Mgl equals kinetic energy rotational. Okay, now the next question is, what is the translational velocity? Specifically, we have to pick a point because each of the points on this rod, now that it has swung down, each point is moving at a different velocity. The bottom is moving faster than the top because, well, it has to. It traveled a greater distance in the same amount of time. It couldn't have made it if it wasn't traveling at a higher velocity. So specifically, I want the velocity of the center of mass. So specifically, what is the velocity of the center of mass? So to get the velocity of the center of mass, all I have to do is take the angular velocity and multiply it not by r. Well, we multiply it by r, but what is our r? So we already said that v tangential is equal to r times omega, but what r are we using here? Well, for the center of mass, r, the distance from the axis, is this over here. It's L over 2. So v of the center of mass is going to be L over 2 times omega final. And we can solve for omega final if we cancel the m's on both sides here, and let's see, multiply by 6, right? 1/2 and 1/3 is 1/6. So multiply by 6 and divide by L squared. Come to think of it, we just have to divide by L because one of the L's also cancels out. So we get L over 2 times omega final squared equals, let's take this and rearrange it over here. Omega final squared equals, we had a G and we're multiplying by 6, so 6G, and we've got an L to divide by, so 6G over L. So omega final is going to be the square root of 6G over L. Square root of 6G over L. Okay, multiply that out. So I'm going to write this as L squared over 4 under a square root. I'm going to say that's square root of L squared over 4 times square root of 6G over L. And now that I have them both written as square roots, I can just put them all under the same square root. So this equals the square root of 6G L squared over 4L. We can reduce an L, and 6 over 4 simplifies to 3 over 2. So this is going to be root 3 over 2 GL would be the final velocity of the center of mass. I probably should have said VCM final in both of these cases. And there you go. Now, some people will ask if we can do something similar to what we did with potential energy. Can we just use the center of mass to figure this out? Can we just take... I'm trying to remember how to word the question. Can we calculate the final velocity of the center of mass by taking a shortcut, by treating the object like this? Can we take this rod and treat it like, here's your axis of rotation again, can we treat it like an object that started at a height of L over 2 and traveled down to, I guess, negative LO2 if you consider the position of the axis to be 0. Can we just treat it like an object of mass m that moved from here to here and calculate the velocity of that object, and that would be the velocity of the center of mass? No, you can't. No, you cannot do that. Can't really do that here. You can't just use the center of mass here because I guess the simplest way to word it is you're gonna be averaging a square of velocities. It's not... I need to word this better if I can. You can't just take... If I chop this rod into pieces, you can't just put all the pieces at the center and say that they all move at some average speed. You can't use the you can't use the average speed to calculate the average kinetic energy of those pieces. If you were to chop this rod into a bunch of pieces and then put all the pieces where the center of mass is, then what you would have is, yeah, I'm not wording this really well. Give me a minute to think about this. So if you think of taking this and chopping it up into pieces, so each piece would be, so I'll draw my axis of rotation over here, and this thing swings. Let's cut it into, I don't know, 1, 2, 3, 4, 5, 6. Okay, we've got 7 pieces here, and this thing swings and it gets to over here, and now you've got 1, 2, 3, 4, 5, 6, 7 pieces again. Probably should have done that in a different color. I probably should have done that in a different color. Well, I'll just highlight it like this. Okay, so this piece is now traveling at some velocity v1, the second piece is traveling at velocity v2, the third piece is traveling at velocity v3, and so on and so forth. And if you think about it, the velocity of each piece is proportional to its distance, so the average of those velocities, if you did v1 plus v7 over 2, that would just be equal to v4. v4 being, piece number 4 being the middle piece, right? The piece that would represent the center of mass. Whatever its final velocity is, you could say v1 plus v7 over 2 is v4, because v1 is simply going to be r1 times omega, and v7 is going to be r7 times omega, and v4 is going to be r4 times omega. But each piece, assuming I chopped it into equal pieces, they were all equally spaced, well, r7 is just going to be 7 times r1. The first piece is going to be one multiple of whatever that distance is, 1/7 of the length, or actually 1/14 if we're being more precise, because you would want to pick the velocity of the center of that piece. R7 would be 7 times R1, R4 would be 4 times R1. So essentially what you have is 1 R1 omega. Here you've got 7 R1 omega. Here you've got 4 R1 omega. And R1 omega plus 7 R1 omega all over 2, that's equal to 4 R1 over omega. So you could do this between V1 and V7. You could also do it between V2 and V6. You could do it between V3 and V5. And then V4 is all by its lonesome. And you might say, well, clearly because the velocities of each of the individual pieces, they vary linearly, the average is just the sum of the velocities over the number of velocities. So it looks like you can get away with it, but here's the thing. You're not going to get the average kinetic energy from the average velocity. Kinetic energy average for a number of pieces that are moving at different velocities does not equal 1/2 m times the average speed squared. The squaring is what ruins it. Even if the velocities vary linearly with distance from the axis, the squares of the velocities do not vary linearly. The squares of the velocities, the first piece is going to have something proportional to 1 squared. The second piece is going to have something proportional to 2 squared. The next piece is going to have something proportional to 3 squared. The next one is going to be proportional to 4 squared, and so on. And if I go ahead and write this all the way out to 7 squared, we said we had 7 pieces, but really it's going to work for any number of pieces you have. If you do 1 squared plus 7 squared, that's 1 plus 49, that's 50. Divided by 2, that's 25. Well, our center of mass is the 4th piece here, and 4 squared, 16, that is certainly not 25. If I do 2 squared plus 6 squared, so 4 plus 36, that's 40. And if I divide that by 2, I get 20. So not only does it not match 4 squared, it doesn't even match 7 squared plus 1 squared. So yeah, the velocity of the center of mass is not going to, or rather the kinetic energy of the rod is not going to just be the translational kinetic energy based on the velocity of the center of mass. Calculating the translational kinetic energy of the center of mass does not give you the rotational kinetic energy of the whole thing, because that would require the kinetic energy at the center of mass to be the average kinetic energy, the average translational kinetic energy of all the individual pieces. I can actually prove this further with calculus, and I've already done so on a sheet that I have lying around that I'm saving for the Physics C students. But yeah, this is, hopefully even without the calculus, you can see what the problem is here. So be very careful. Do not try to abuse center of mass to calculate final kinetic energy for a non-point mass. For shapes like this that have some fraction in their moment of inertia formula, it's not going to work. You have to do it this way. You have to use rotational kinetic energy. You can't just substitute it with translational unless you're willing to do calculus and figure out what the average translational kinetic energy is for each of the individual pieces. If you cut this into infinitely many pieces and get their total translational kinetic energy, that's the same as the rotational kinetic energy of the rod. That's the same as the MGL that we got earlier. So basically, just use moment of inertia. Moment of inertia basically has that calculus built in so that you don't have to do it. Using moment of inertia and using rotational kinetic energy already takes care of the whole averaging out of the kinetic energies of all the individual moving parts of the rod or whatever swinging object you may have here. So that is all I have to say about that problem for now. For the Physics C students, we will revisit this with calculus later. And by later, I mean definitely not today. In case some of you are new here, I am going to be covering the calculus-based part of the course after finishing everything algebra-based, because that's the way I like to teach it. I know some of you are sick of hearing me repeat things, but we have newcomers every now and then, and they might not be up to speed. They might, for whatever reason, start from this stream, and that's why I need to constantly give out these reminders, because they may not have heard all the stuff I said in the previous streams. I would recommend, if you are new here, to go back and look through those previous streams. Even if you know all the topics, I have a lot of warnings and recommendations and best practices and stuff, so you might want to go through that. Better to do it now before AP exam week creeps up. Oh, I can't wait to see how Reddit is going to look as AP exam week creeps up. Although, to be honest, I'm already seeing posts like, is it possible to learn all of AP whatever in this many weeks remaining before the AP exam? Those posts are hilarious. I mean, at that point, are you really learning anything? Yeah, technically it's possible. There have been people who have done that. They're just really good at guessing, and they are really good at this sort of shallow learning and, giving the graders what they want to see. But did that person actually learn anything? I would say no. Real learning does require some time, so any study hacks, I saw a video pop up recently, sometime this week. There was something about, I think it was titled like how to study so fast it feels illegal or something like that. I didn't click on it. I don't care what that person says. I don't care what their ideas are. Those promises are never going to be delivered on. There's no such thing as faster studying. There's only studying while cutting out things that you think are unimportant, which will probably turn out to be important later. So yeah, give your courses the amount of time that they actually deserve to be learned properly. That's enough of Al's philosophy corner. Let's get back to physics. So now that we know about rotational kinetic energy, there is a classic problem of comparing multiple objects rolling down a ramp. I like to call it the amazing race. Okay, here is the amazing race. So we are going to have, as our contestants, a ring or hoop. A ring. We are also going to have a solid sphere. Of course, there's no way you can visually tell if this is solid or hollow unless I just specifically tell you. And for our third contestant, we are going to have a cylinder or disc. And these three objects find themselves situated on top of a ramp. I guess I didn't draw the angle of that ring very well. But these three things find themselves situated at the top of some sort of ramp. I'm drawing it a little more 3D this time around. And they are all released at the same time from rest. We will say that the height of the ramp is big H. And the questions are typically as follows. Which one arrives at the bottom first, or which one is the fastest? Both are actually going to be the same answer. Whichever one is moving the fastest by the time it gets to the bottom must have also gotten to the bottom the fastest. If they all started from rest, that's just kind of common sense. So, which one arrives at the bottom the fastest? Which one has the most kinetic energy, that is total, both translational and rotational? And what is the ratio of translational to rotational kinetic energy? among the three. So I will give you some formulas that you're going to need. For a hoop, moment of inertia is just mr squared. For a sphere, a solid sphere, I sphere solid, rotating, of course. Well, what is the axis of rotation for these? So that's something I didn't talk about last time. If an object is not being held down by something, if it's not being physically held down by a hinge or some physical axis, if this ruler isn't being held down, if I don't swing it along an axis like this, if I don't have some sort of axis holding it down, if I just toss it into the air, if I just throw it with a little bit of a twirl, what is the axis of rotation going to be, do you think? Once again, it's the wondrous thing known as center of mass. An object's natural axis of rotation is its center of mass. Unless you restrain it in some way, unless you force it to rotate around some other axis, an object will naturally rotate around its center of mass. And why is that? Well, we explained last time that the center of mass of an object is where you have the least moment of inertia. That's the axis through which moment of inertia is a minimum. That is the axis through which rotation occurs most easily. That's where you will get the fastest rotation for the torque that you have. So naturally, an object, as it starts to pick up speed, if it tries to pick up speed, on some axis off of its rotation center, then it's going to resist spinning around that axis. So it will just naturally, over time, find itself spinning around the axis for which it gains the most angular velocity for that torque. It might initially, depending on how it's thrown, or if it's not thrown, how it's caused to rotate, it might initially attempt to rotate around some off axis. Actually, I'm not entirely sure about that. I probably shouldn't state that as fact. I'll have to think about that one. I will have to think about that one. But the bottom line is, whether or not there is any initial motion around some other axis, eventually is going to pick up the most speed around an axis going through its center of mass, and that is where it will just continue to rotate until something stops it. That is the axis around which an object naturally tends to rotate. So for all of these, the axis of rotation is just going to be through their center. So I sphere solid, for an axis through its center, is going to be 2/5 of its mass times its radius squared, and then for a cylinder or disk, again through its central axis, is going to be 1/2 mr squared. You don't have to memorize these for the AP exam, but I would definitely recommend memorizing the hoop because it's simple enough, and the cylinder because the cylinder shows up in a lot of problems, and maybe also the rod through its end for reasons that I went over last time, because you can use it to calculate moment of inertia for rods through any other axes, as long as you know the one for the rod through its end. But yeah, cylinders, very common to approximate things as cylinders. You will have, like, this yo-yo could be approximated as a cylinder or disc, for example. You might have a problem involving something like that. Pulleys are often approximated as cylinders or discs. Some tires might be approximated as a cylinder or disc. So you're just going to see a lot of book problems if you go through your book, and also the OpenStax book that I link to in the course plan. Actually, I haven't read through all those problems, so I can't speak for that one, but any decent textbook will have a number of problems where you have to approximate things as cylinders. So I think it would be to your benefit to try and commit this to memory. You might end up naturally doing it anyway without even trying, just because you're going to see it so much. At least you should, if you're practicing a good enough number of problems and your source of those problems is a decent source of problems. But now I'm rambling. So let's go ahead and figure out what the final translational velocities of the centers of masses are going to be. The velocities of these rolling objects are the translational velocities of their axes. The velocities of their centers of masses are what I'm trying to find, because, well, that's where their axes of rotation are. So I'm going to find the center of mass for each object. And I guess before we talk about how to solve this, we need to establish an understanding of rolling without slipping. These objects are going to roll without slipping. Rolling without slipping. I knew I was getting ahead of myself. Rolling without slipping. Okay, so let's take something like a disc. And we'll get back to this problem in a minute. Well, more than a minute, but you know what I mean. So let's say we have something like a cylinder over here, and it begins rolling. So there are two, well, I guess 3 different ways it can move. One way is it could just strictly slip. I'm going to pretend this thing is a cylinder. So one thing it could do, instead of doing this is rolling without slipping. Notice how it's perfectly smooth motion. The object's axis of rotation moves in tandem with the object rolling. There is no skidding or slipping. Versus one thing it could do, if this was like on a steep slope, if this was on, let me see, I guess maybe I could use my book if I can get it to a steep enough angle. If you get it to a steep enough angle, you should be able to see the object not roll so much, and instead it will just slide like this instead of rolling. Or what it will probably do, again, I need to make the slope really steep for this, and it's probably going to be too quick to see on camera anyway, but if you make the slope steep enough, that's still not steep enough, I guess that was, then what you'll see is this sort of rolling interrupted by slipping. Better yet, here's an experiment you can do at home that's relatively safe. Actually, I would recommend not doing it at home, but like, outside on a not very busy street, maybe in a parking lot or something. Take a water bottle or something that's just shaped like this, tube shaped, and give it a kick. Take something like a water bottle and give it a kick, and you'll see what happens with it is it'll probably lift off of the ground a little bit, and then it'll come back onto the ground, and it'll kind of skid a little bit and then jump, and then skid a little bit and jump, and with every jump, or rather in between those jumps, it does start to rotate, and eventually it goes and then starts, and then lands and starts to just smoothly roll from that point on. So that's something you can observe in real life. Take a water bottle, fill it with water, give it a kick, and try to kick it, try to kick it where you can actually generate some torque. Don't kick it directly towards its center of mass, because then you're strictly going to get translation. Well, actually no. You would still get rotation anyway, because you'll get torque caused by friction. And come to think of it, if you kick it this way, yeah, I would kick it closer to the top rather than the bottom. I would kick it closer to the top rather than the bottom, just to give it some initial torque, and that will help it get to this sort of smooth rolling state sooner. But for rolling without slipping occurs when the object's center of mass, let me use a different color for this. Let's use U. No, we already used that color earlier on this page. Let's do this one. So rolling without slipping occurs when the velocity of an object's center of mass is equal to the tangential velocity on the rim of the rolling object. Well, actually, that's not going to be the whole truth if the object is rolling without slipping. So if the object was just spinning in place, if the object was just spinning in place, whatever tangential velocity the rim of the object has when it just spins in place rather than rolling, if the center of mass is moving translationally at that same velocity, then that's when rolling without slipping occurs. So whatever the velocity of the center of mass is, that is one velocity that the whole entire object has. That is a part of the velocity that the entire object has. So every point on this object is going to have a velocity center of mass. Whatever this is the translational velocity of the whole object. So I'm going to call this V tran. So every point on this object is going to have this velocity V tran. But on top of that, every point except for the center of mass, every point except for the center of mass is going to be rotating around the center of mass and is going to have an additional velocity on top of this V tran. So that additional velocity can be calculated by simply using the formula for V tangential. V tangential equals R times omega. V tangential equals R times omega. So you're going to have a V tangential over here at the top. Let's say that this thing rolls clockwise. Then V tangential at the top would be this way. V tangential at the bottom would be this way. V tangential over here would be pointing up. V tangential on this side would be pointing down. And so on and so forth. So rolling without slipping occurs when this V tangential is equal in magnitude to this V tran, this velocity of the center of mass. What happens at this point is, well, over here, this V tangential, if it's equal in magnitude to V center of mass, then the velocity at this bottom point that's touching the ground, the total velocity is going to be 0 here. These would be equal and opposite. They would cancel out. And you can actually see this if you take an object and make it roll and watch it in slow motion. You would be able to see that the point, whatever point is in contact with the surface that the object is rolling on, isn't really moving. It's waiting for the rest of the object to kind of just swing around it. It's a very blink and you'll miss it sort of thing. But if you record it on a camera and then really play it in slow motion, then you might be able to observe that. You might be able to observe that the bottom point isn't really, it's not slipping, right? By definition. It's not moving translationally. The point that's in contact with the surface doesn't rub against the surface like this. It just kind of lifts off of the surface. It just, I'm going to use my finger here as the surface. It just kind of lifts off of my finger. Maybe I should mark the point. Actually, no. Here's what I'll do. So we'll say the point is right under the tip of this arrow. So watch how, yeah, it lifts off. It doesn't slide against my finger. It just lifts off and gets replaced by some other point that is now the new point in contact with the surface. So all this is to say, rolling without slipping means V translational equals V center of mass equals V tangential equals R times omega of the object. Whatever the radius of the object is, whatever the angular acceleration of that object is, that will be the translational velocity of the object, which you can use to calculate the translational kinetic energy of the object. Okay, now that we have that established, we can say what? Well, the V center of mass, why did I write this here? I'm trying to go backwards in my mind and figure out what I was going to do here before we went on this rolling without slipping detour. I think it was compare VCM for each object. Is just going to be R times omega for each object. Well, I didn't really give you the masses of any of the objects or their radii. Guess what that means? They are not going to matter. Once we do the math, we're going to see all of that stuff cancels out. We're going to see that all of that stuff cancels out. So, if I draw a sideways view of any one of these objects, if I just draw a sideways view, let's say this is the disk, for example. It could be any of the objects, but let's say we're looking at the disk sideways here. What does the force diagram look like? What does the force diagram look like? Well, we're going to have, I don't want to use orange for this, let's use red. I'm going to have a normal force. I'm going to have a force of gravity. I'm going to have a static friction force. We actually need a static friction force for this to work. This will not work on a perfectly smooth surface. We need to have a static friction force, and I guess that's everything. So is the energy conserved here? You might think because of the presence of the static friction force that it's not. We know with the normal force, if the object is just moving this way, then the direction of the displacement is perpendicular to the normal force anyway. So normal force times whatever this displacement is times cosine of 90, work done by normal force is 0. Work done by gravity, that's conservative, so we don't even need to worry about that. What about work done by the static friction force? Well, by definition, we said rolling without slipping, right? By definition, the velocity of whatever point on the object is in contact with the surface at any given time, the velocity of that point is 0. If you have no velocity, you have no displacement of that point along the direction of the whole object's motion, and more importantly, along the direction of the static friction. There is no displacement. You'd have force of static friction times 0 displacement, and then this point doesn't even slide against the surface, it just lifts up and gets replaced by another point, and that other point then just lifts off without sliding against the surface, and so on and so forth. So there's actually no work being done by the static friction force. There is no net work being done by the static friction force either. So mechanical energy is conserved here. We can say mgh initial plus, well, there's going to be 0 translational and 0 rotational kinetic energy, and there's no springs here, so we don't have to worry about that. Plus the non-conservative work, well, that's 0. Equals mgh final, which I will set to 0. I'm going to say that potential energy is equal to 0 here at the bottom. Potential energy gravitational is 0, so we'll set that to 0. Plus 1/2 m VCM squared plus 1/2 I omega squared. That'll be the equation for each of our 3 objects. So if I go ahead and make my substitutions, I'm going to do one for the hoop, one for the sphere, and one for the cylinder. We're going to have, H initial is just going to be big H, so mg big H equals 1/2 m v center of mass squared plus 1/2, let's see, for the hoop, I is just going to be mr squared. And omega squared, I'm going to replace that very much like I did with, was it our previous example? I know I did it somewhere here for our previous example. Yeah, over here. V equals r times omega, or in other words, omega is equal to v over r, and this v tangential, for rolling without slipping, v tangential is equal to v center of mass. So I can actually just replace it with v center of mass over r and square it. And from that we get an r squared, which cancels with another r squared, and we're left with mgh equals 1/2 mv center of mass squared plus 1/2 mv V center of mass squared. A half and a half add up to a 1. You can cancel the m, and then you're left with V center of mass squared equals GH. You're left with V center of mass squared is equal to GH. So V center of mass is equal to square root GH. Okay, let's do the sphere. Let's do the solid sphere now. So mgh equals 1/2 m V center of mass of the sphere squared plus 1/2 for a sphere, for a solid sphere rotated about its central axis. It's going to be 2/5 mr squared for its moment of inertia. 2/5 of its mass times its radius squared. Now, I should probably be naming these m hoop and V center of mass hoop and R hoop. I should probably be giving these masses and radii their own different names so that I'm not assuming that they're all equal, but it doesn't matter. It's not going to matter because all of these m's and r's are going to cancel out anyway for this problem. But in a problem where they didn't cancel out, yeah, I would try and name them in such a way that I keep them distinct from one another. Anyway, times omega squared, which is just going to be, again, V center of mass over R squared. The r's cancel out, or rather the r squared cancels out with this r that gets squared. The masses all cancel out. And we are left with GH equals 1/2 plus a half times 2/2 is 1/5. So 1/2 plus 1/5. And then all that's left out of this is VCM squared. Yeah, at the very least, I should probably name the V's differently. This one is the sphere, VCM sphere squared, VCM hoop squared. And then a half plus a fifth, that's 5/10 plus 2/10 is 7/10. So that equals 7/10 VCM sphere squared, and multiply by 10 over 7 on both sides. VCM sphere squared is equal to 10 over 7 GH equals VCM sphere squared. And following that same pattern, we can do one more. Let's do the cylinder. So we have, yet again, mgh equals 1/2 m VCM of the cylinder squared plus 1/2 for a cylinder. Moment of inertia is 1/2 mr squared. I don't know why I was blanking on that. And then omega squared of the cylinder is going to be V center of mass over R all squared. This R squared and this R squared will cancel out. The m's all cancel out. And I'm left with GH equals a half plus half of a half, so 1/2 plus 1/4, that's 3/4. So I'm getting GH, I guess I'll write it up here. I'm getting GH equals 3/4 VCM cylinder squared. Multiply by 4/3 on both sides, and I'm getting 4/3 GH equals V center of mass of the cylinder squared. So, of course, there's a remaining step of taking the square root on each side, but even without taking the square root, this is enough for us to compare them and answer the question, which one arrives at the bottom first? We've got 1 GH, we've got 1 3/7 GH, and we've got 1 1/3. 3/7 is more than a third. So I'm going to say the sphere is the one that arrives at the bottom first. We also could have figured this out just conceptually from recognizing that the sphere has the lowest moment of inertia out of them all. The sphere has the lowest moment of inertia, has the lowest resistance to rotation, so it rotates the most easily. What this means is that its rotational kinetic energy costs less, which means more of its kinetic energy gets to stay as translational rather than rotational. The less moment of inertia an object has, the less rotational kinetic energy is required to get it to rotate in tandem, to get it to roll without slipping, which leaves more of its kinetic energy to be available for translation rather than rotation. So that's just an idea that I want you to take away, something that might come in handy for quickly answering maybe a multiple choice question instead of having to math it all out. I mean, I want you to be able to do the math, but on a test when you're pressed for time, if you can just conceptually determine without having to do any math, if you can just quickly answer, I don't know, choice C, the solid sphere would be the one that wins the race. If you can understand this idea conceptually, then that will definitely help you on the exam. I'm not against taking shortcuts, I'm just against taking shortcuts without understanding them. Right? We talked about this. I can't remember the last time I brought this up, but my rule for shortcuts is if you're going to use them, make sure you understand them. Don't just use a shortcut formula that you found online that you don't know the origins of, that you don't know the proof for. Make sure it's proven. Make sure you understand the proof. If it's not your proof, then make sure you understand the proof, and better yet, after sleeping on it for a week or so, see if you can redo the proof yourself. If you can't, you probably shouldn't be using it. Okay, was there another question I was asking here? Right, the ratio of the rotational to translational kinetic energy. We can actually compare that pretty easily. So each of these has a rotational kinetic energy of 1/2 mv squared times what? Times the fraction part in front of their moment of inertia formula. So if I do kinetic energy rotational over kinetic energy translational for each of these objects. For the first object, it's 1/2 mv squared over 1/2 mv squared. So it's going to be 1/2 and then some fraction, I'll just call it f, and then mv squared. And the translational is just 1/2 mv squared. So the 1/2 mv squared cancels out everywhere, and all you're left with is that fraction. That is the ratio of rotational to translational kinetic energy. So this, again, reinforces what I was just saying. The lower the moment of inertia, the lower the amount of rotational kinetic energy you need. relative to translational. The solid sphere requires a rotational kinetic energy that is 2/5 of whatever translational kinetic energy it has. So if you basically you would have 2 to 5, so you would have, basically you would take the total kinetic energy and divide it into 7 portions, and you would give 2 of those portions to the solid sphere, to the solid sphere's rotation, and 5 of those 7 portions. Wait, is that right? Yeah, and then 5 of those 7 portions would go to translational kinetic energy. You get 5 portions of translational kinetic energy for every 2 of rotational. Pretty efficient compared to the other ones. The hoop demands a 1-to-1 ratio. The hoop demands absolute equality and fairness. And then the cylinder is just kind of in between the two. The cylinder is willing to settle for half, so I guess with the cylinder, the kinetic energy would be divided 3 ways. One piece for rotation and 2 pieces for translation. And I think that is everything that needs to be said here. Is there anything else I wanted to comment on regarding these? I don't think so. Let's go ahead and look at some problems in the book. Oh, I see. Right. I did say we were going to do that problem, so I'll remember to do that one. But first, let's do like 1 or 2 problems where we can use the concept of rotational kinetic energy a little bit. Just get comfortable with it. So this one says, a 10-kilogram cylinder rolls without slipping on a rough surface. At an instant when its center of gravity has a speed of 10 meters per second, determine the translational kinetic energy of its center of gravity, the rotational kinetic energy about its center of gravity, and its total kinetic energy. Actually, that's pretty simple. It's basically the reverse of what we just did. It's giving us the velocity of the center of mass and asking us to work backwards from there. Oh, no. Backside of that is already used. Time for a new sheet. Alright, so they said it's a 10-kilogram cylinder. I didn't draw that well. Oh well, you know what it's supposed to be. So it's a 10-kilogram cylinder, and it rolls without slipping on a rough surface at an instant when its center of gravity has a speed of 10 meters per second, so V, center of gravity, center of mass, either way, they're the same thing as long as you're close to the surface of Earth. That's 10 meters per second. And it says determine the translational kinetic energy, the rotational kinetic energy, and its total kinetic energy. So find kinetic energy translational. Find kinetic energy rotational. And find kinetic energy total by just adding up the two. Notice that they did not give us the radius of the cylinder. What are the odds that it's not going to matter? Pretty high. Okay, so they do expect us in this book to just look up or have memorized that moment of inertia for a cylinder is, well, we just saw it, 1/2 the total mass of the cylinder times its radius squared. So let's see, kinetic energy translational would be just 1/2 times 10 KE translational is 1/2 times 10 times the velocity is also 10 squared. So that's going to be 1/2 of 1,000 is going to be 500 joules. Oh, that's something we need to do too. Let's check out the units for rotational kinetic energy and make sure that they actually check out. So kinetic energy translational, 500 joules. Kinetic energy rotational is going to be 1/2 times 1/2 times 10 times r squared times omega squared. Omega squared is going to be v squared over r squared is going to be 10 squared over r squared. The radii cancel out. And I'm left with half of 10 times 100, half of 1,000. That is 1/4 of 1,000 or 250 joules. And the total kinetic energy is 750 joules. Okay, that problem was actually a lot easier than I thought it would be given its paragraph length, but okay. Here's another one that might be a little bit better. Oh, actually, before that, let's not forget. Do the units of rotational kinetic energy check out? The units of kinetic energy rotational. Let's see, we have 1/2 I omega squared. The 1/2 is unitless, so that's not going to do anything for us. And then I and omega squared. Okay, well, moment of inertia has units of kilogram meters squared. So the 1/2 I'll just leave out. And then we've got kilogram meters squared times units of angular velocity is radians per second. The radians aren't true units. Remember that. Basically, you could treat it as just a 1 over here. Replace radians with the number 1 if you want. And we get kilogram meters squared times 1 over seconds squared. So we get kilogram meters squared per second squared. Are those joules? Well, we could do kinetic energy translational. That's 1/2 mv squared. Kinetic energy translational, we know that's in joules. Equals units of mass times units of regular velocity squared. That's kilograms times meters per second squared. That's kilogram meters squared per second squared. So yeah, it checks out. this is indeed a joule. I probably didn't need the brackets here or here or here. The brackets mean units of, and kilogram, meters squared, and radians per second don't have units. They are units. So yeah, I don't actually need the brackets there. I should have just used parentheses. Details, details. Okay, now we can look at our next one. So the next one says, use conservation of energy to determine the angular speed of the spool shown in the figure. I will draw it for you. After the 3 kilogram bucket has fallen 4 meters starting from rest, the light string attached to the bucket is wrapped around the spool and does not slip as it unwinds. So I will read that again after drawing the figure. So what they have is a bucket I guess here's its handle, and it is tied to a string, rope, cord, whatever you want to call it. And that rope runs along a spool, basically a pulley. I didn't draw it very well, but this thing has an axle drawn through it. It has an axle running through it. And it's rotating this way, so the bucket is being lowered. So it says, use conservation of energy to determine the angular speed of the spool shown in the figure after the 3 kilogram bucket has fallen 4 meters starting from rest. The light string attached to the bucket is wrapped around the spool and does not slip as it unwinds. And I see we are nearing the 2-hour mark, so I think angular momentum is being saved for next time. Anyway, bucket is 3 kilograms. And it has fallen 4 meters starting from rest, so we'll say that it started somewhere up here and has fallen 4 meters. V bucket initial, VB initial is equal to 0. And that would also mean that omega initial for the spool is also 0. The light string attached to the bucket is wrapped around the spool and does not slip as it unwinds. Very important to mention that the string doesn't slip as it unwinds. That means that the string is moving at the same velocity as the bucket. So the velocity of the string, which is the tangential velocity of the spool, since it doesn't slip against the spool, that's the other thing. The string is moving at the same velocity as the bucket as it's being lowered, and because it doesn't slip on the spool, that must mean that the spool is moving with the same tangential velocity as the string. That's the only way for it to not be slipping, is for the relative velocity between the rim of the spool and the string to be 0. That means they must be moving at the same rate. That means tangential velocity of the spool. I don't know why I struggled to get that word out. Tangential velocity of the spool must be the same as the velocity of the string, which is the velocity of the bucket. And also, there's something more over here. They did not say this in the wording of the problem, but it is written on their diagram. The spool is 5 kilograms and has a radius of 0.6 meters. So those are some additional details that we will need. And of course, they didn't say it outright, but we are going to approximate the spool as a solid cylinder. And the axis of rotation we can see here as just going through the axis of symmetry. So it's going to be a 1/2 mr squared again. That's I cylinder. I don't know why I didn't specify that in the previous problem. But there we go. So let's write out our conservation of energy equation. In this case, energy is not conserved for the bucket individually or for the spool individually, but together their total, did I say kinetic energy? Mechanical energy. Together, their total mechanical energy is conserved. Because you've got this force of tension here, which does do negative work on the bucket, since it pulls up on the bucket and the bucket moves down, but it also does positive work on the spool, and the total work across the two should cancel out. So your total non-conservative work is 0. We will talk about how the string does work on the spool once we look at the next problem. We can talk about how to actually calculate it if you wanted to stop and calculate and confirm that they're going to be the same. But for now, we'll just take it for granted that this is the case. Work non-conservative of the system is equal to 0. So mechanical energy of the system is going to be, well, the spool doesn't really have a change in its gravitational potential energy. So whatever height the spool is at, that's not going to change. It's at that height in the beginning, and it's going to stay at that height in the end. Whatever mgh you assign to it, you'll have the same mgh on both sides of the equation, and it'll cancel out. But I'll put it in our mechanical energy equation just for the sake of pointing it out. So m spool G H spool plus, I guess that would be H spool, let's say initial, plus M bucket times G times H bucket initial plus 0 translational kinetic energy for the spool, 0 rotational kinetic energy initial for the spool, 0 translational for the bucket, and 0 rotational for the bucket. I know it's kind of redundant because there's no way that this bucket is rotating, but again, just for the sake of putting it all in there. And there are no springs here, so no elastic potential energy to take into account. Okay, after, and I guess plus non-conservative work of the bucket plus non-conservative work of the spool, non-conservative work of the system, in other words, which is another 0. Okay, equals m spool, I should have just called it ms, G H spool final. Well, H spool final and H spool initial are the same, so these are going to cancel each other out. Plus M bucket G times H bucket final. Plus, for the spool, no translational kinetic energy, but there is, plus 1/2 I omega squared for the spool. And then plus, there's going to be 1/2 M bucket V squared plus 0 rotational kinetic energy for the bucket. Let's make our substitutions. So we've got 3G. I'll say that this height is 0. I'll say this is where potential energy gravitational is equal to 0. So that means that H bucket initial is going to be positive 4 if I count positive as being the upward direction from this line. So that's going to be 3 kilograms times G times 4 plus, well, nothing is left on the left-hand side, plus mass of the bucket is 3 kilograms again times G times 0. Should have substituted that as a 0 from the get-go. I don't know what I was thinking. Plus 1/2, that's going to be 1/2 mr squared for the spool. So that's going to be 1/2. Its mass is 5 kilograms and its radius is 0.6. Times its angular velocity squared. Whatever its angular velocity is squared, that's the translational velocity over the radius squared. So that's going to be V over 0.6 squared. It's the same V as the bucket has. So that's your 1/2 I omega squared taken care of. The 0.6 actually cancels out, so we didn't even need the radius. And then plus 1/2 mass of the bucket times V squared. So plus 1/2 times 3 kilograms times V squared. So we have 12G on the left equals half of 5. So 1/4 of 5 is 1.25. 1.25 V squared plus half of 3, that's 1.5 V squared. So that's 2.75 V squared. So V squared is equal to, take your 12G divided by 2.75 and then take the square root. Since we've made it this far, we might as well plug it in and see what number we get. 12 times 9.8 divided by 2.75 and then take the square root, and I get 6.539. I'll say 6.54. So we get V is approximately 6.54 meters per second. Is that what it was asking? Use conservation of energy to determine the angular speed of the spool. Okay, now we need the radius of the spool. That's why they included it. So omega of the spool is going to be V over R, is going to be 6.54 over 0.6 And that's going to be 1 point something, 1.09, right? 6.54 divided by 6. Yep, 1.09 radians per second equals 1.09 radians per second. That's around 60 degrees a second. Just doing some quick mental math there, it's approximately 60 degrees. Very rough approximation, but somewhere around that much, right? Because 2 pi radians, that's 6.28 radians, would be a full circle. So this is about a sixth of that. A sixth of a circle is about 60 degrees. Well, a sixth of a circle is exactly 60 degrees, but I'm saying about 60 because this is about a sixth, not exactly a sixth. A little less, actually, right? Or no, actually it would be a little more. A sixth of 6.28 would be about 1.0405-ish. Anyway, let's take a look at this question over here that introduces the idea of work being done by a torque. Let's take a look at work being done by a torque. So it says a constant torque of 25 Newton meters is applied to a grindstone whose moment of inertia is 0.13 kilogram meters squared. Using energy principles and neglecting friction, find the angular speed after the grindstone has made 15 revolutions. The hint says that there's an angular equivalent to total work equals net force times delta x equals 1/2 mv final squared minus 1/2 mv initial squared, and that we should convince ourselves that the relationship is correct. They wrote what the rotational version of the relationship is, but I don't want to give it away. Let's try and figure it out. So we have net work or total work, however you want to name it. That's equal to the total force times the displacement times the cosine of the angle. We'll say for the sake of simplicity that cosine theta is equal to 1 for this problem, just to keep things simple. Well, net work is equal to what? It's equal to the change in kinetic energy. It's equal to 1/2 mv final squared minus 1/2 mv initial squared is what we learned. That's our work kinetic energy theorem. Well, what about the rotational equivalent? So it would still be work on the left-hand side, except this time we would have net torque instead of net force. And instead of linear or translational displacement, we would have angular displacement. And here we would have 1/2 I omega final squared minus 1/2 I omega initial squared. We need to prove this relationship. Because all we did just now is take an equation we already knew and replaced some variables in it. That's not really a proof. We need to actually sit down and prove this. So let's see what we can do. I'm going to start with net torque times delta theta and see what I can do with that. So net torque times delta theta. Well, I know net torque is equal to I alpha, right? This is the rotational counterpart to Newton's second law. So I'm going to do I alpha times delta theta. Okay, I'm seeing where the I is coming from. Alpha delta theta, that should look familiar to you. If it doesn't, then what about A times delta x, or delta y for that matter? That should be conjuring up memories of your kinematics equations. Alpha delta theta is in our third kinematics equation. So that equation was omega final squared equals omega initial squared plus 2 alpha delta theta. So if I subtract omega initial squared and divide by 2, then I get 1/2 times omega final squared minus omega initial squared equals alpha delta theta. We subtracted omega initial squared and then divided the whole thing by 2, which is the same as multiplying the whole left side by 1/2. So that is alpha delta theta. And you can probably see from that immediately now that, yeah, it's going to be 1/2 and then I'm going to have, so it's going to be I times 1/2 omega final squared minus omega initial squared, so 1/2 omega final squared minus omega initial squared, all times I. Distribute the I and the 1/2, and there you go, 1/2 I omega final squared minus 1/2 I omega initial squared, or in other words, kinetic energy rotational final minus kinetic energy rotational initial, or delta KE rotational. That's really the main part of the problem that I wanted, but I guess we can solve the actual numerical problem that they gave us. So they said we have a constant torque of 25 Newton meters, and it's the only torque. If it's the only torque, then by definition it must be the net torque. The sum of only one torque is just that one torque. Net torque equals 25 Newton meters. I was reading the other thing, and that doesn't even say 15, it says 13, so I mixed both of them together somehow. 25 Newton meters is the net torque, and the object's moment of inertia is 0.13 kilogram meters squared. Using energy principles and neglecting friction, find the angular speed after the grindstone has made 15 revolutions. Delta theta is 15 revolutions. This relationship that we just discovered only works in radians. Apart from our kinematics equations, you should always be in the habit of converting your rotational variables to radians. Your angular velocity, your angular displacement, your angular acceleration, they should be in radians. The only exceptions where you can get away with not using radians would be in rotational kinematics. We discussed which cases those were and what happens if you don't use radians in those cases. And the other one is going to be coming up when we discuss angular momentum. which from the looks of it is pretty much definitely going to be next time. So delta theta, they said, was 15 revolutions, 15 revs. That's where I got the 15 from earlier. That's why I thought it was 15 Newton meters. Okay, I'm not going crazy. Or maybe I am, just not at the rate that I thought I was. 15 revs. 1 revolution is 2 pi radians. So just multiply by 2 pi radians over 1 rev, and you get 30 pi radians. And from there, we can just do 25 times 30 pi equals, let's see, was it initially at rest? They didn't say anything. They said, using energy principles and neglecting friction, find the angular speed after the grindstone has made 15 revolutions. I'm just going to assume it started from rest because they didn't give us anything else. Yeah, that has to be the assumption, but they didn't really indicate that super clearly in any way. Usually they're pretty good about stating when something is at rest. So we're going to do 25 times 30 pi. That's your torque times delta theta, equals 1/2 I, so 1/2 of 0.13, times omega final squared minus omega initial squared. Omega final squared minus, well, 0 squared, since we're assuming it's at rest. And let's see. I guess, yeah, we would plug in pi. There's nothing we can simplify over here anymore, so we'll go ahead and plug in the value of pi. 25 times 30 times pi. And then I'm going to multiply by 2 to cancel the 1/2 and divide by 0.13. So times 2 and divided by 0.13. And then if I take the square root of that, omega final is 190.39. Omega final equals 190.39 radians per second, which is pretty fast, but it's a grindstone, so that's not entirely surprising. Those things are supposed to spin fast. Let me see if there's anything else here that I want to cover. I feel like there's a type of problem that I am forgetting to go over. Let me see if I can find something in the other book, because I'm kind of blanking right now. on what else needs covering. That's rotational kinematics. Here's rotational dynamics. Let's see what you have for me. Oh, I think I remember there was a good multiple choice question here somewhere. Let's see. This might be the one. Give me a minute to read it. Okay, here we go. This one might be good to end off with. So it says, consider 4 objects all solid spheres. Sphere A has radius r and mass m. Sphere B has radius 2r and mass m. Sphere C has radius r and mass 2m. Sphere D has radius r and mass 3m. It says all can be placed at the same point on the same inclined plane where they will roll without slipping to the bottom. The answer to the following questions might also be E, all are the same. So E, all are the same. And they have 3 questions. All are the same. Might be a possible answer. So basically this scenario, but everything is a sphere. They just have different masses and radii. So question A, which object has the largest rotational inertia? Well, they're all going to be 2/5 mr squared, so the 2/5 part doesn't matter. All that matters is the r's and the m's. So let's take the m's, multiply them by r squared, and see which one wins out. Here you get mr squared. Here you get m times, if you square the 2r, you get 4r squared. So this is 4mr squared. So far this is the winner. Here you've got 2m times r squared, so not 4, not enough. And here you've got 3m times r squared. B definitely wins there. So B has the highest moment of inertia. Highest I, it would be B. Okay, second one is asking, if released from rest, highest. Why do I do that? I forget the last letter at the end of a word I'm trying to write. I don't know how that happens. Highest I. Part B, or second question rather. If released from rest, which object will experience the largest net torque? largest net torque experienced by which one? Which one will experience the largest net torque? If they are released from rest. Well, I guess first we have to figure out what is the angular acceleration going to be for each of them, because net torque is moment of inertia times angular acceleration. So how do their angular accelerations compare? The one with the greatest angular acceleration would be the one that needs to experience the greatest amount of torque. Actually, even if all of their angular accelerations are the same, the one with the highest moment of inertia would need the highest torque. So I guess we need to figure out, first of all, how do their angular accelerations compare? Well, we already did this sort of problem, and we saw that it doesn't matter what the mass and radius of the sphere is, the final velocity of the sphere at the bottom, if it rolls without slipping, is square root of 10 over 7 gh. So if all the spheres are going to have this same velocity, then it stands to reason that they would all accelerate at the same rate as well. So they all have the same angular acceleration. So if alpha is the same for all of them, then what about net torque? What about I alpha? If alpha is the same for all of them, then the difference in their net torques has to be due to the difference in their I's. The one with the highest I would have the highest need for torque in order to keep up with the others. So the answer is B again. And then third question, if released from rest, which object will experience the largest linear acceleration? Well, they all have the same angular acceleration, so they should also all have the same linear acceleration. They're all going to have the same angular velocities at the bottom. They're all going to have the same linear velocities at the bottom. They're all going to roll down in the same amount of time, since they're all going to have the same angular acceleration. So it follows that they should also have the same linear acceleration. So all are the same. So greatest linear acceleration, greatest, I guess we'll call it acceleration of the center of mass for brevity. All of them should be the same. Oh, there's a fourth and fifth question for the same scenario. Hold on. If allowed to roll down the incline, which object will have the largest speed at the bottom of the incline? We already talked about this. They're all the same. Largest speed, VCM, all the same. And then the fifth question, if allowed to roll down the incline, which object will reach the bottom of the incline in the shortest time? Which one will reach the bottom in the shortest time? And the answer is yet again E. All of them are going to be the same, because the speed changes with the height for each sphere at the same rate. So at each and every height you visit along the way down the incline, at each and every height, when they start here, they're all at rest. When they come down to here, they all reach the same velocity, whatever their velocity is here, when they get to this height, they have the same velocity. So at every single height, at every single point along the way down, they should have the same speed. So they're just moving together. They're moving at the same speed in the same amount of time with the same acceleration. So again, it is choice E. Let me see if I can find something. Oh, I just saw it. I just saw it. Aha. Yes, this over here. Yeah, this is something that I said we were going to discuss a long time ago. I'm glad I lingered around a little bit, or else I would have forgotten to do this. Okay, so it says, in an Atwood's machine, which is basically just a pulley system, in an Atwood's machine, one block has a mass of 512 grams, and the other a mass of 463 grams. The pulley, which is mounted in horizontal frictionless bearings, has a radius of 4.9 centimeters. When released from rest, the heavier block is observed to fall 76.5 centimeters in 5.11 seconds. Calculate the rotational inertia of the pulley. Here we go. So I said a long time ago when we did pulley problems that we were making an assumption that the tension on both sides of the pulley was approximately the same. Today we're going to learn why that's not the entire truth, and why assuming that the pulley is light and frictionless actually helps to justify doing that. So we just have, I guess I'll draw it over here since there's nothing better to do with this space. So we have, I guess it's connected to a ceiling somehow, and you have a pulley over here. And then connected to the pulley will be two objects. One object here, one object here. So they said one of them is 512 grams, the other is 463. So this one will be 512 grams, this will be 463 grams. Converting them to kilograms, it would be 0.512 and 0.463. Then they say the pulley, which is mounted in horizontal frictionless bearings, has a radius of 4.9 centimeters. So radius of the pulley is 4.9 centimeters, or 0.049 if converted to meters. I don't know why I started circling that. When released from rest, the heavier block is observed to fall 76.5 centimeters in 5.11 seconds. So S distance is 76.5 centimeters, or 0.765 in meters. And T is 5.11 seconds. Calculate the rotational inertia of the pulley is the question being asked. What is the moment of inertia of the pulley? All right. So, force diagrams. We've got two different tensions this time. I'll call this force of tension right, and I will call this force of tension left. Force of tension left is also exerted downward. The reaction to it, force of tension left, is exerted downward on this side of the pulley, and force of tension right is exerted downward on the right side of the pulley. And of course there's going to be a force of gravity. I should draw it actually bigger than the tension force. That doesn't look bigger, but oh well, I tried. Force of gravity, I guess we'll call it force of gravity right. And this will be force of gravity left. And yeah, there's a force of gravity on the pulley itself, but that's canceled out by the normal force from the axle or bearings that are holding the pulley. So those two forces are going to cancel out. Since they act at the center of the pulley, they're not going to create any torque. The center of the pulley is where your pivot has to be, because that's the point around which the pulley will spin. So yeah, both of those forces are acting at the pivot. They will create no torque. Even if they did, they're equal and opposite, acting at the same point. Even if they were acting at a point that wasn't at the axis of rotation, as long as they acted at the same point, they would create equal and opposite torques that cancel out. If one of them was acting like on the right side and the other is on the left side, then in that scenario, even if they were equal in magnitude, their torques would not necessarily cancel out. In fact, they would add. But yeah, they both act at the center, so no net torque due to either of those. We don't have to worry about those two forces. I'm not even going to bother labeling them. Anything else that I'm missing? I don't think so. So let's go ahead and see what we can do. We can first figure out what the angular acceleration even is. Angular acceleration will be the first thing we need to find, and we should have enough information to figure it out because the system started from rest, so omega initial should be 0. The radius of the pulley is 0.049 meters, so I'm going to figure out what arc length, what delta, or not, we have the arc length. I'm going to figure out what angular displacement the pulley experienced. So all I have to do is say S is equal to R delta theta, where delta theta is in radians, of course. That's the only way this equation works. And divide by R. S divided by R would give me delta theta. So 0.765 S over R equals delta theta. So 0.765 over 0.049 equals delta theta equals how much? 0.765 over 0.049 is about 15.612. 15.612 radians. 15.612 radians. Okay, so now I have delta theta, I have omega initial, and I have time. I can get the angular acceleration. Best way to go about that would probably be the second equation of kinematics. So I'm going to do delta theta equals omega initial times t plus 1/2 alpha t squared. That's going to be 15.612 equals, well, that's a 0 because omega initial was 0. equals 1/2 alpha times 5.11 squared. Multiply by 2, divide by 5.11 squared. So 15.612 times 2 is 31.224, divided by 5.11 squared. 5.11 squared is going to be a little over 25, 31 over that. I should be expecting something around like 1 1/5, 1 1/4. I'm getting 1.1957. That's about 1 1/5. So yeah, alpha is equal to 1957, so I'll round to 196. 1.196 radians per second squared. Now that we have that, we can also just multiply this by the radius to get the translational acceleration of the blocks. So I'm going to go ahead and do that. A tangential is equal to r times alpha equals 0.049 times 1.196 equals how much? 0.049 times 1.196 is about 0.0586. Is about 0.0586, and that should be, I multiplied by meters, so I should be getting meters per second squared. All right, let's switch colors. How about green? So next up is what? We've got the translational acceleration. So I can write my net force equations for each of the blocks now and figure out what their tensions are. So I can write net force equations for each block. For the 512 gram block, that's the one that goes down. So I'm going to say down is positive for this block, while up is positive for this block. So positive direction is basically going to be like this. Up around the pulley and then down on the right side. So force of gravity right, that's going to be, let's see, 0.512 kilograms m times a. So m times 0.0586, right? Net force equals MA equals forces down minus forces up, so that's going to be 0.512 G minus force of tension right. Add force of tension right to both sides, subtract 0.512 times 0.0586 to the right hand side, force of tension right equals, I can factor out 0.512 and then G minus 0.0586. Probably not going to be that big of a difference from G itself, but 9.8 minus 0.0586 is 9.7414. This is why we usually treat these tension forces as being equal. The difference is probably going to be really small. As to whether or not it's negligible, I guess that's a matter of opinion. It certainly wouldn't be negligible if you were working for NASA. 0.512 times 9.7414 is 4.98759. I'm going to round that to 4.99. I wonder if that's even going to be enough decimals. we'll go with it for now, 4.99 newtons, and hope that that's enough decimal places to see a difference between it and force of tension left. Speaking of force of tension left, let's write the net force equation for the block on the left. So it's going to be mass times acceleration, 0.463 times 0.0586 equals up minus down this time, so force of tension left minus force of gravity left, so that's 0.463 times g. Add 0.463 g to both sides, and I'm going to get force of tension left equals 0.463 times 0.0586 plus g, which is going to be what, 9.8586. So 0.463 times 9.8586 is going to be 4.564. Okay, that's actually a noticeable difference. So force of tension left equals 4.56 newtons. I'll just round it to 2 decimal places like I did with the other tension. Okay, that's not a negligible difference between the two. That's actually what? If I subtract the 2, that's going to be 40.43 over 4.99, 0.43 over 4.99. That's about 8.6% difference. That's not that negligible. Maybe if it was under 1%, or maybe even 2%, you could argue for it, but here there's not much room for arguing. 8.6% is fairly significant. It's noticeable. So now we know the tension on both sides of the pulley. This is great. Now we can figure out the net torque on the pulley. So net torque on the pulley is going to equal its moment of inertia times its angular acceleration. So net torque is going to be torque due to tension right and torque due to tension left. I already decided that clockwise is the positive direction, so tension right is going to cause a positive clockwise torque. Tension left is going to cause a negative or counterclockwise torque. So it's going to be torque of tension right minus torque of tension left. Torque of tension right minus torque of tension left. And we already said earlier that these other two forces on the pulley create no torque around the center. And for the moment of inertia of the pulley, it'll be 1/2 of its mass. Oh, wait, actually, we don't know its mass. So we don't have to treat the pulley like a cylinder. Actually, what we can do is once we find this moment of inertia, we can try and see if dividing it by r squared gives you... Actually, no, we couldn't do that. If we knew its mass, we could then confirm. If we knew its mass, we could do its mass times r squared and compare that to 1/2 mr squared and see if the I that we get from here is even remotely close to it. And then we could see just how close to being a cylinder it actually was, or if it was just straight up a cylinder. But yeah, we can't do that without knowing the mass. Oh well, missed opportunity. But I suppose if they did tell us the mass, this would have been a trivial problem, right? We would have just Well, no, it wouldn't be trivial because we wouldn't be assuming that the pulley is a cylinder in this case. Yeah, I'm going back to saying it was a missed opportunity for them writing this problem. It was a missed opportunity. They could have given the mass of the pulley and asked how accurate would approximating the pulley as a cylinder be given the moment of inertia that you found in part A. They could have done this as a part A and part B, and then in part B, suppose the mass is whatever number. Would it be appropriate to approximate the moment of inertia of this pulley as a cylinder or disk? Why or why not? Justify your answer. All the classic phrases that you see in word problems, book problems, free response questions. So anyway, I times, what was our alpha again? It was 0.0, no, that's the translational acceleration, 1.196. 1.196 for alpha. Okay, torque of tension right minus torque of tension left. Well, the force of tension just acts tangent to the pulley, and it will just act at, some point on the rim of the pulley, and the displacement from the pivot of that point is just going to be one radius away, and the radius has to be perpendicular to that tangent. It has to be perpendicular to that tangential direction. So your pivotal displacement, as I like to call it, is just going to be the radius of the pulley. Multiply that by the force of tension. So you've got R times force of tension right minus R times force of tension left equals I alpha. Come to think of it, if you wrote alpha as A translational over R, you could then, I guess, multiply the R over to the left-hand side and get an R squared. I think there is a problem. I'm blanking on which type of problem it would be, where the R's, I think, cancel out, but I'm not entirely sure. I might be misremembering something. Anyway, 1.196 again. I can factor out the R here and just do 0.049 times force of tension right minus tension left, so 4.99 minus 4.56. Okay, and now the rest is just calculator work. So the moment of inertia is 0.049 times, the difference between those is 0.43, so times 0.43, and then divided by 1.196. And I'm getting 0.0176. 0.0176 kilogram meters squared. There we go. There we go. Now I think I've covered everything I want to cover. At least I hope I did. There are going to be some other types of problems that I haven't shown here today. You will see some of them in the worked example videos that I always link in the course plan. If you don't know what I'm talking about because you're new here, check the link in the description. I've got the course plan over there. If you just click open under each of the different chapters, it expands and opens up like a list of topics, and if you scroll to the bottom of each list for each chapter, unit, whatever you want to call it, you will find links to things like playlists and other resources, simulations, files that might have practice problems, especially for some of the earlier chapters, and a list of problems that I would suggest looking at in the book. The book is linked at the top. It's the free OpenStax textbook. Not a perfect textbook by any means, but if you don't have a textbook, you might as well look there. And even if you do have a textbook, having another source of extra practice problems can't hurt. So yeah, any problems listed in the course plan are referring to that OpenStax textbook specifically. It's the second edition for those of you in the far future watching this after they've made newer editions. They still have, you can still access their first edition, actually. You have to do some digging around to find it, but I would assume if they come up with a third or fourth or fifth edition that you'd still have some way of accessing the second edition. Probably what'll happen is people will just start having their own saved PDF copies and sharing those with each other online through Google Drive links or whatever, because that's how the internet is. And I mean, it is meant to be a free resource, so it wouldn't be illegal to do that. The textbooks are open source. But yeah, that is it for me. Oh, actually, let me give you a problem or two to look at. What should I give you? And I guess I can do this one. This one, it's very easy to overthink this one. And I say that from experience because the first time I did it, I was overthinking it too. And probably the next 2 or 3 times after that. But they have a block of mass M over here, and you guessed it, a pulley. And another block also of mass M over here. They said the tension in this part of the wire is T1, the tension in this part is T2, the moment of inertia of the pulley is I. They just called it I. And it says 2 identical blocks, each of mass big M, are connected by a light string over a frictionless pulley of radius R. So the radius of the pulley is R. And rotational inertia I. The string does not slip on the pulley, and it is not known whether or not there is friction between the plane and the sliding block. So coefficient of friction over here. Is there even friction at all? We don't know. Unknown. Could be frictionless. There could be some friction. We do not know. Unknown if friction is present. When this system is released, it is found that the pulley turns through an angle theta, so delta theta, they simply called it theta. Delta theta equals, they just called it plain old theta, in time t, and time equals t, okay? Or maybe to be more precise, delta t equals t. And the acceleration of the blocks is constant, as one would assume. So part A is asking, what is the angular acceleration of the pulley? It's got three parts. Part A, what is the angular acceleration of the pulley? Or honestly, I could just say angular acceleration, period, because the blocks are certainly not going to be the ones with the angular acceleration. Part B is asking, what is the acceleration of the two blocks? So what is the translational acceleration? And part C, what are the tensions in the upper and lower sections of the string? So part C, what is T1 and what is T2? And for all answers, express in terms of, M, I, R, theta, G, and T. That last part especially is gonna be a bit of a headache because you can easily overthink it. But go ahead and try that one, and we will look at it at the beginning of next time. I'm not entirely sure when next time is. Maybe I can squeeze it in on Saturday and still have something for Sunday. Because let me think. So the next stream is going to be angular momentum, and then I would like to do one more stream after that, which is just kind of mixed review problems of the whole rotational dynamics chapter, and then go to simple harmonic motion. So if I can do all that Saturday and Sunday of this week, that would be great. But we'll see. Assume that we don't have anything before Sunday, but if I manage to find a way to fit it in, then maybe we'll have an extra on Saturday. But that is it for me today. Hope you benefited from this and learned something useful as always. And remember to keep practicing, and don't just aim for an A, aim for mastery. It's not just about the grades. Getting grades can make things easier for you in life, but what matters the most is actually learning something. So keep studying, make sure you're following all of the advice and guidelines I've been giving throughout these streams, for those of you who've actually been watching all of them, and hearing all those guidelines. And the AP exams are coming, so it might be a good idea to start reviewing. Maybe make a short list of the stuff that you think you could understand better. Even if you are confident about something, try to look for some challenging problems. You know, if you feel like you're on top of your kinematics, I would encourage you to go and challenge yourself to find problems that you look at it and you don't immediately know how it's going to play out, and then you start working it out, and then you realize, there's more to this problem. Those are the problems that you want to look for if you feel like you've already mastered a particular chapter. So basically every chapter is going to have something for you that's worth learning and reviewing. Just because some chapters are a higher priority than others doesn't mean that you completely neglect the lower priority ones. But yeah, that is it for me today. Class dismissed.